Okay, so the last two sections of chapter 10, which is on so-called conic sections, we do not cover. This means we are entering chapter 11 today, and I'm going to start with 11.1. We're not going to complete 11.1 today. We will start it. Okay, let's get started. Okay, so what I'd like to talk about is 11.1, and this is part 1 of 11.1. And this is about sequences. And what's a sequence? A sequence is a list of numbers. So it's usually notation is we denote the numbers maybe A1, A2, where you have a subscript, A3, A4, etc. Or maybe you want to start at A0. It doesn't really matter. And usually we use the notation, a compact notation, where the braces indicate you have the set of all A sub n's. And sometimes we want to emphasize where the index is ranging over, so it will be A sub n goes from 1 to infinity. So these are all the same, these are all notations for the same thing. So let's talk about some examples. So what about the sequence 1 over n? That's the sequence 1 over 1, comma 1 over 2, 1 over 3, 1 over 4, dot, dot, dot. Okay, let's try another example. N over n plus 1, that would be the sequence 1 over 2, 2 over 3, 3 over 4, 4 over 5, etc. Then we have another example, minus 1 to the power of n over n, and that would be the sequence n is 1, you get minus 1 over 1. When n is 2, you get plus 1 over 2, minus 1 over 3. Oops, that doesn't belong there. 1 over 4, minus 1 over 5, etc. Okay, let's try one more. Let's try sine of n pi over 2. Well, this is just the sequence. When n is equal to 1, you get sine pi over 2, so you get 1. When n equals 2, you get sine of pi, which is 0. When n is 3, you get 3 pi over 2. Sine of 3 pi over 2 is minus 1. Then we get 0, and then we get plus 1. Let me put signs in. 0, minus 1. So it's alternating. It's either plus 1, 0, or a minus 1. Okay, so that's a sequence. Dot, dot, dot. All right, so I'm going to give you one more example, but I need to clear the screen to do that. Okay, it's called the Fibonacci sequence, which has all sorts of interesting applications in mathematics. It goes like this. You start off with the number 1, and the next term is 1, and then you take those two terms and add them together to get 2. Then you take 2 and add the previous 1 to it to get 3. Then you take the 3 and add the 2 to it to get 5, and then 5 plus 3 is 8, and 8 plus 5 is 13, and 13 plus 8 is 21, etc. Dot, dot, dot. So we can actually figure this out as a sequence in general. F sub n is the sequence given by f sub 1 equals f sub 2, and then f sub n equals f sub n minus 1 plus f sub n minus 2 if n is at least 3. So this is actually how to figure out the sequence. Okay, so that's an example. Another example is gotten by taking functions. So if let f of x be a function on the real line, and so we can make a sequence out of it by setting a sub n equal to the value of the function at the non-negative integer, at the positive integer n. So what is the sequence? We could denote this sequence by f of n. And so this is f of 1, f of 2, the value of the function at 2, the value of the function at 3, etc. Okay, so for example, an example of this kind would be f of x equals x squared. So this would be the sequence 1 squared, 2 squared, 3 squared, 4 squared, etc. Okay. Now, the primary thing we're interested in when talking about sequences are limits of sequences. Okay, so let's let a sub n be a sequence. Then we are interested in computing the limit of the sequence is the limit as n goes to infinity of the numbers a sub n, and if that number is L, if L exists, if the limit exists, this limit exists, we say the sequence converges to L. Oops, that's really ugly. Converges to L. If not, the sequence diverges. That's what we say. And sometimes, if this is a special, this is a sort of an additional case that sometimes matters. If a sub n, if the limit of a sub n is infinite, if a sub n tends to infinity, then we write the limit as n goes to infinity, a sub n equals infinity. This limit exists, but it's not a finite number, so it also kind of diverges, but it diverges in a very particular way. Okay, so now I want to talk about some properties of limits of sequences. So I need to clear the screen. So properties of limits of sequences. And these should not be surprising because you learned about limits before. So I'm going to talk about several properties. So first of all, the limit, oops, one, the limit of a sum is the sum of the limits. So limit, if you have two sequences a sub n and b sub n, we can look at the limit as n goes to infinity of a sub n, b sub n, and this will be the same as the limit as n goes to infinity of a sub n plus the limit as n goes to infinity of b sub n. But we need to require, we're assuming here that the limits exist. Okay, so that's the second thing. That's the first thing. So similarly, the limit of the difference will be the difference of the limits, assuming the limits exist. Third property is that if we take a constant and multiply it by a sequence to get a new sequence, that the limit as n goes to infinity of multiplying it by a constant, you can bring the constant through the limit sign, assuming, again, the limit exists. Quotients behave similarly. If you have two sequences, you could take the quotient n goes to infinity. And for this to make sense, the b sub n's can never be 0, of course, because fractions over 0 don't exist. And then this will be the limit of a sub n over the limit of b sub n as n goes to infinity. I will not put the notation in entirely. If we're assuming here the limit of b sub n's is not 0. Okay, so these are basic, obvious properties. Now we get to a very important property, which is called the squeeze property, or the squeeze theorem. So that's property 5. It says this: assuming a sub n is less than or equal to b sub n is less than or equal to c sub n, and the limits of the a sub n's as n goes to infinity are equal to some number L, which is the same as the limit as n goes to infinity of c sub n, then the limit of the middle sequence also exists and is given by L. In particular, the middle sequence will converge if the outer sequences converge to the same number. Okay. Okay, so here's an application of the preceding. Suppose, so if the limit of the absolute values of a sequence is equal to 0, then so is the limit as n goes to infinity of the original sequence given by 0. And here's the reason. I'm going to use the squeeze property. The number a sub n is less than or equal to its absolute value always. And it's also greater than or equal to minus its absolute value. So now the right-hand term by assumption, this is an assumption here, that's an assumption, this term on the right goes to 0. Likewise, by one of the properties, putting a minus sign in front of a sequence which converges, you can bring the minus sign through, but the absolute value converges to 0, so minus the absolute value of the sequence converges to 0. So now we have the squeeze theorem. So that means that the limit as n goes to infinity of a sub n must be equal to 0 by the squeeze property. Okay. All right. Now, the remainder of this lecture, I just want to do a couple of examples, okay? And I'll call it a day. So it's going to be a relatively short lecture. Okay, so first of all, let's consider the following example. Let's consider the sequence ln of n over n, the limit as n goes to infinity. I'd like to compute this limit. Now, if I just let n go to infinity, what's inside doesn't seem to do anything obvious. However, we're going to use the following fact, which is another property, maybe. We should call it property 7. If a sub n is f of n, where f of x is a function, and the limit as x goes to infinity of f of x equals L, then so does the limit as n goes to infinity of the value of the function at the integer points. Okay, so I'm going to use that property. So therefore, in order to compute this limit at the top, that's the same as the limit as x goes to infinity of ln of x divided by x. So now we can convert, this is now a function in the sense of, a curve, ln of x over x. And now the point is that ln of x over x, when x gets very big, this is an indeterminate form. of type infinity over infinity. This is one of those forms that enables you to apply L'Hopital's rule. So the limit as x goes to infinity of ln of x over x is the same as the limit as x goes to infinity of the derivative of the numerator, which is 1 over x, divided by the derivative of the denominator, which is 1. So that as x goes to infinity, you're going to get 0, right? So therefore, our limit, the limit of the sequence, is going to be given by 0. Very good. Okay, so let's do another example. This next example is actually kind of important. So let's let R be any real number, and let's compute what happens to the limit of the sequence of taking powers of R. Okay, so this would be the sequence R squared, R cubed, etc. Okay, so the answer is going to depend upon what value R is on the number line. So what's going to matter is on the number line are the points -1. These are the boundary points of the answer. And we'll see what happens when R is bigger than 1, less than -1, etc. So let's first of all take the case where R is bigger than 1. If you have a number bigger than 1, so that would be somewhere here on the number line, then taking powers of it, it blows up. So this diverges. It tends to infinity, in fact, okay? So what happens if you take a number strictly, what if R equals 1? Well, then you're taking powers of 1. That's a constant sequence with value 1. So the limit is 1. Okay, so what happens when R is actually -1? When R is -1, then you're going to be having an alternating sequence, -1, +1, -1, +1. So this sequence is jumping up and down. It's oscillating between -1 and 1. It doesn't converge to anything. It diverges. Okay, so now let's take values of R, which are between 0 and 1, let's say. Positive numbers then. And what happens to a number like a fraction 1/2 when I take powers of it? As the powers get bigger, like 1/2 to the billionth power, you get a very small number. That limit is tending to 0. So we're going to get 0 as the limit. And then if R is between 0, in fact, we can let R equal 0. If R is between 0 and -1, but not including -1, by the squeeze theorem, I'm going to leave that argument out, you also get 0. Powers of any number whose absolute value is strictly less than 1, in other words, will give you 0. Lastly, what happens when R is less than -1? Then the powers of R, depending upon whether they're even or odd powers, it's blowing up to a very large power that's going to oscillate between a very large number and an extremely small number, negative number, like plus a billion, minus a billion, etc. It's going to oscillate, so this diverges. So the answer is the limit as n goes to infinity of R to the n is given by 0 if the absolute value of R is less than 1, 1 if R equals 1, and it diverges otherwise. Okay, so that's an example. Okay, I'm going to do one final example today, which is the sequence nth root of n. Okay, so this is actually kind of hard to analyze directly, so I'm not going to analyze it directly. I'm going to do something. So I want to calculate the limit as n goes to infinity of the nth root of n. Now, this is actually the same as the limit as x goes to infinity of x to the 1 over x power. It's the xth root of x. Now, here's what I'm going to do. I'm going to think of the x to the 1 over x as e to the power of ln of, do I want to do it this way? Yeah, I want to think of it as e to the power of ln of x1 over x, which is the same as e to the power of ln of x divided by x, because x to the power of 1 over x brings the 1 over x outside. So now I want to first analyze ln of x over x as x goes to infinity. Well, we saw that by L'Hopital, this tends to a value of 0, right? Because let me repeat the argument, ln of x over x, that limit as x goes to infinity is the same as the limit as x goes to infinity of 1 over x over 1, which is 0. Okay, so that tends to 0. So therefore, e to the power of ln of x over x tends to e to the power of 0, which is 1. So therefore, the limit as n goes to infinity of the nth root of n is going to be the same, is going to be 1. And that is the final answer to the last exercise. So that's our short lecture for today. We'll continue with this section in my next lecture.